So here we are. We made it to the end of the chapter. So this last section, we're going to be talking about solids and only about solids, and specifically crystalline solids. I showed you earlier what a crystalline solid was and what amorphous solid was. And let's begin with these two questions. What is the difference between intermolecular forces and intramolecular forces? So the key word inter and intra. For example, if I have water, which we already know is a polar molecule, partially negative, partially positive, the forces keeping the atoms together within the molecules, those are my intramolecular forces. However, if there are more than one molecule present, like it always is, the interaction between the partially negative and the partially positive that's what we call a intermolecular force. So a pretty important distinction, because intramolecular forces are going to be what we know as the ionic bonds or the covalent bonds. Not to be confused with the hydrogen bond intermolecular force, because that's really not a bond, that's an attraction. So the bonds, the forces that are really bonds or intramolecular forces are going to be the ionic and the covalent. This one within the intramolecular forces, this one being the weak, and this one being the strongest one. And you already know the relationship between the intermolecular forces: dispersion, dipole, hydrogen bonding, and ion dipole. So that's the difference between intermolecular forces and intramolecular forces. The strongest of the forces, the ion dipole, does not compare in strength with these intramolecular forces. These intramolecular forces are way up there on their leagues. The intermolecular forces, those are important forces, but they're weak compared to the intramolecular forces. So now that we have that distinction made, because it's going to be important to understand the solids, excuse me, in terms of forces, what is the main difference between solid, liquid, and gases? Well, we know if I show you this, and I show you this, and I show you this, and I tell you between A, B, and C, which one is the gas? And you will say, C is the gas because the particles are farther away from each other. This will have to be the solid, and this will have to be the liquid, because you already know that the phase of matter, solid, liquid, gas, depend on the forces keeping those molecules attracted to each other. So the solid would have the stronger forces, right? And we're talking intermolecular forces. Strongest. This one will have the stronger. And this one will be the weaker, or the weak compared to the other two. So let's keep that in mind. When we talk about solids, we're talking about the strongest forces that there are, And there's going to be a blurry distinction between intramolecular and intermolecular forces. So let's check that out. So when we talk about solids, and we're just talking about crystalline solids, we're not talking about the amorphous, there's going to be three types of solids: molecular solids, ionic solids, and atomic solids. Molecular solids, like the name implies, is going to be made out of molecules. Two or more elements put together. Ionic solid is going to be made out of ions, cations and anions. And atomic solid is going to just contain atoms of the same thing. So it's not going to be a molecule where you need two or more atoms, or most of the time different atoms. Atomic solid is going to be just atoms put together somehow, and most of the time the same atom. So for a molecular solid, you should be able to say, there's a molecule, there's a molecule, there's a molecule, and they're very close together because of the intermolecular forces, and they're making a solid, like ice. A molecule of water with another molecule of water and million molecules of water below 0 degrees Celsius, that's going to make a solid, which we know as ice, but it's made out of molecules. So it's a molecular solid. Salt, like the one you're seeing here, is made out of sodium chloride. And we know that sodium is a metal and chloride is a non-metal. The sodium loses an electron becoming a cation. The chloride gains an electron becoming an anion. So it's made out of ions. A metal, usually a metal and a non-metal. So those are going to be my ionic solids. And because the attraction between a positive charge and a negative charge is a lot stronger than an attraction between a partially positive and a partially negative. So this would be a intramolecular force, and this is a intermolecular force. So this one is the strongest one. Intra is always stronger than intermolecular forces. So every time you see a metal with a non-metal as part of the formula, you're dealing with a ionic solid. What about atomic solids? Where atomic solids have a subdivision, and you're going to have covalent solids. But notice that I didn't say molecule. And the reason is that you can have silicon, which have 4 valence electrons, joined to another silicon with 4 more valence electrons, joined to another silicon with 4 valence electrons, joined to another silicon with 4 valence electrons, joined to another silicon with 4 valence electrons, joins to another silicon with 4 valence electrons. And you can imagine this going in all directions, even toward you. And it's like a network. So what we're doing is a network. But everywhere they cross, there's a silicon in there. So the thing holding them together is a bond between 2 silicon atoms. Silicon is a metalloid, kind of facing the non-metal side. So we're going to call this a covalent bond. So that's what we call these solids, covalent. It's not like ice, which is made out of a covalent compound, because ice, you will have a molecule attracted to another molecule by intermolecular forces, attracted by other molecules by intermolecular forces. Here you have silicon bonded intramolecular to another silicon, bonded intramolecular to another silicon. So that's what we call this a covalent atomic solid. We also have the non-bonding atomic solid. What would that be? Let's say that we take a gas, an noble gas. Noble gases do not link with anything because they have 8 valence electrons already, like xenon. Xenon, we have 8 valence electrons. So if I put another xenon close by, they cannot bond because they have all the 8 electrons already. However, because these have electrons, they're going to be moving, and that's going to create dispersion. So these gases can make solids just because of the dispersion forces. But it's going to have to be under extreme amount of pressure. They're going to have to be a system putting a lot of pressure, forcing those gas molecules that want to be farther away from each other, putting them super close together. So it's going to have to be a lot of pressure and very, very low temperatures. But you can get a solid out of a noble gas. But the only thing keeping them together is intermolecular forces, dispersion. So you can put on your memory bank that the non-bonding atomic solid is made out of noble gases. I do not know of any other example that is not noble gases. So those are going to be your non-bonding, because they already have 8 electrons, atomic solids, kept together by dispersion force, very, very low temperature to slow down those gases into solids, and a lot of pressure to keep them together. And then the other atomic solid is going to be the metallic, which is made out of metal. For example, a piece of iron, a silver spoon. Anything made out of metals is going to be an atomic metallic solid, because it's made out of the same element over and over and over. So keep that chart handy. I will give it to you on the test. You just need to know the terms so you can understand what you're looking for. So let's do that with this problem. Identify each solid as molecular, ionic, or atomic. When I look at the first one, all of them are going to be solids, by the way. We're forcing them to be solid using temperature and pressure. So assume that all of them are solid because we're telling you so. So the first one is a noble gas. So that gotta be a non-bonding atomic solid. So the first one is an atomic solid. What is non-bonding? H2O is a molecule, so that's going to be molecular. K2O is an ionic compound, so that's going to be ionic. Not that difficult, right? This one is just iron, which is an atom, so it's going to be atomic metallic, so just atomic. This one is a metal with a non-metal, so ionic. This one is a molecule, so that's going to have to be molecular. This one is another metal, nickel, transition metal, so that's going to be atomic. Remember, the only atomics are going to be the metallics, the noble gases, sorry for that, and the ones that make network, like diamond, graphite, silicon, stuff like that. And this one is a molecule, so this is also molecular. Because notice there's only 2 of them, right? So that's not a network. There's only two of them, just a molecule of I2 attracted by dispersion forces to another molecule of I2, and so on, and so on, and so on. The only thing keeping them together is the dispersion force. How do I know it's only dispersion force? Because this molecule is nonpolar. So there's no dipole anywhere. So that's how you classify the different type of solids. So remember, molecular, ionic, or atomic. And if you're not sure about the atomic, check the subtable that tells you more about that. So, based on that, if I wanted to say which one has the stronger forces, I will start with the ionics, strong force. Then I will look at the atomics. The atomics, the metallic is super. How many of you have tried to melt iron? It's super, super hard. So I would say the atomic metallics are also strong. That's also strong. I would say the atomic noble gas, the non-bonding, only dispersion force, that's going to be one of the weakest solids. So as you bring it out of those conditions, will become a gas right away. And then the molecular, you have to be careful. Molecular, and molecular. The first molecular is water with hydrogen bonding. So these are going to be weak. But the weakest one is going to be carbon dioxide, which is nonpolar, so therefore only dispersion. Water is going to have dispersion, dipole, and hydrogen bonding, so that's going to be stronger than CO2. And iodine is going to have also strong forces within the weak forces, because even though it's only dispersion, it has a molar mass of around 240 grams per mole. So that's going to make it into a solid also. So you bringing together everything that you have learned so far. So with that said, go ahead and do that daily work. And once you're done with that daily work, we're gonna look at this pair of solids and we're gonna see which one have the higher melting point. Higher melting point means the strongest forces keeping them together, so you have to apply more energy to separate one from each other. So we're gonna have to classify what they are. This is gonna be an atomic solid, it's an over gas. And this one is gonna be a metal, so atomic also, but metallic versus non-bonding. Non-bonding should tell you that it's very weak. So the higher melting point is going to be the metallic. The second one, this is a molecule, so this is going to be molecular. And this is also molecular. We saw earlier that this one can do dispersion, same with this one. We saw that it was bent, so dipole. Same with this one. But this one could also make hydrogen bonding. So this one will have to be the one with the higher melting point. Then we have atomic non-bonding because it's an over gas forced into a solid. This is also atomic non-bonding, another noble gas. So what's going to make the difference is going to be their size or their mass. So which one weighs more? Xenon is below krypton, so xenon will be the biggest one, which means the dispersion forces are gonna be stronger than this one. So xenon would be the one with the higher melting point. And then for the last one, we're gonna have ionic and molecular. So definitely the ionic would be the one with the higher melting point. So that's how we do that. So make sure you read more into that on the textbook for more detail, but I think you can handle with what we have been discussing together. So make sure you go ahead and do that daily work. So daily work 12.9, but at the beginning we have some that were 12, 1A, 1B, and C. So you're gonna have close to 15 problems to do for this chapter. And with that, I'm gonna say that you have a pretty good idea now of how to identify crystalline solids in terms of being ionic, molecular, or atomic. And if they're atomic, they can be covalent, non-bonding, or metallic. And with that said, quick review. We talk a lot about what differentiates solids from liquids and gases. We have a whole chapter on gases before this one. We start talking about intermolecular forces, and we saw how they define surface tension and viscosity. We also talk about vapor pressure when we were talking about the evaporation and condensation process. Then we went into melting, freezing, and sublimation, and we did calculation with all of them using the heat of vaporization and the heat of fusion. Then we went deeper into the 4 intermolecular forces. We determined how to figure out what forces are going to be prevalent based on the Lewis structure, the shape, and so on. And we were able to relate that to the strength or the melting point or the boiling point, and now we apply everything into solids. And this one we didn't discuss it because you did a whole group discussion just on water, and you saw all the unique properties of water. And with that, we are done with this chapter. Good thing, because I'm losing my voice after a whole day recording these lectures. So it's been a pleasure, this chapter. So let's get ready. Next week we go into chapter 13, followed by chapter 14, and we are done. So hang in there. Take care. See you soon.